Good morning, good afternoon. Welcome to a new year, and I thank you for joining us. This is Mark Richardson with Vibrant Technology, and we have another MEscope ODS Videos Webinar on tap for you today. Today we are going to look at some new ODS-FRF capabilities in the ODS video software, and we are also going to give you a sneak peek at a new interface called MEscopeNXT. This is a new interface for currently for ODS videos and future MEscope VES down the line, but for now we're focusing on ODS videos, so you'll get a sneak peek at that. Again, thanks for joining us, and I'm joined by Dan Ambray with Full Spectrum Diagnostics. Couple of housekeeping items before we get going here. We are going to keep everybody on mute for the duration of the webinar. If you have questions, feel free to type those questions in the questions dialog box in the Go to Webinar panel on the right side of your screen there. And we will try and get most of those or all of those questions answered, certainly by the tail end of the webinar. Incidentally, we are recording this webinar, so if there's something you do miss, you will get a link to the recording of the webinar, and as well, we will post this webinar up on the Vibrant YouTube channel. I encourage you to take a look at the YouTube channel. We have a full catalog of all of our past webinars, so you can go out there and view any of them, and there's a lot of good content, not only on ODS videos, but also on MEscope VES and modal analysis, and boy, there's a ton of stuff on there, model building, so on and so forth. With that, let me hand things over to Dan, and we will get going.
Hello, everybody. My name is Dan Ambray from Full Spectrum Diagnostics, and we got another webinar in store for you today. The front page here that you're probably looking at is MEscope VES versus MEscopeNXT. The VES software is Visual Engineering Series, is soon to be replaced, at least the video portion of that, with the MEscopeNXT or NXT software. And I was skeptical because I've been using the VES software for a really long time. But with the MEscope product on there, or the videos on there, it's just a little cluttered. The way this works, the MEscope VES software has all the ODS and modal and acoustics and finite element. And so it has just a ton of menus in there. And if you're not well versed in that, it can be overwhelming. It's hard to find the proper command every once in a while. The NXT version cuts all that out. So it is only MEscope videos. So that's the only thing we're processing with it right now. And it has a little growing pain right now. We're getting little bugs fixed and making things nice and friendly for the user. And I was a little skeptical, but I played with it for a couple days, and I think I'm hooked. So it's a nice interface, and I think there's going to be some really good improvements. My standard message is the paragraphs on the left there. Many production-related machines and drive systems cannot be shut down or interrupted to complete a modal or resonance type analysis. In this case, operating deflection shape can provide insight into the motions of the machine during normal operation that cannot readily otherwise be seen or interpreted. The ODS video software is a high-speed video vibration analysis. The video clip is processed with something called the optical flow algorithm. This algorithm enhances the subtle displacement and rescales the amplitudes. This process allows the user to see what the human eye can't perceive on its own in a video animation, either because the event is too fast or the displacements are too small, or both. So it's a nice format for getting a quick look at a piece of machinery. And it's not the end-all be-all. There are some other things we can do for that, the traditional ODS analysis, the modal analysis, and et cetera, that is going to get us to the correct answer. But this is really becoming something nice. and very helpful right off the bat. So let's explore a little bit of it. We're going to do a comparison of MEscope VES and NXT, showing you on the same machine, kind of how the menu system works and how they're producing pretty much the same answer. And you'll see how that works out. Uh-oh, kind of locked up. There we go. So this is the VES shell. We get into the Vibrant software, MEscope ODS Videos, and from here we can make a project to do anything that the software wants to do. We're going to choose videos. So at the top here, there's a drop-down box, and we'll click on ODS, new ODS video, and we bring up the video wizard. And I have this horrible looking dark machine on the right side here. I'm going to clean that up. So this is adjust and crop. There's a couple things that are a little more difficult when you do high-speed video. At 1,000 frames per second, you can't get enough light. This thing was lit up like a spotlight with all my LED panels pointed at it, and it's still a dark machine. Okay, and that's just a function of the high speed and indoor conditions and not having enough light, basically. Some applications it works great, some doesn't. We can adjust the brightness and contrast, and that's going to help us out lightening this up, and you'll see that in a moment. If it comes in rotated 90 degrees, you can, if you take the camera and you need a long shot top to bottom, you can rotate the camera, which gives you the best look at your machine, but it'll come in that it needs to be rotated. So we can easily remedy that situation. If it occurs, we can adjust the brightness and contrast, and we can crop the video. This one has a little tag at the bottom. So there's a time of 8.259 seconds, something like that. And as you play the video, this thing will change. So it's counting as you're going. We need to crop that out because that is vibration. In the video world, it's changing, it's causing a change in the pixel colors, and it changes that to motion in the time waveforms, and it'll affect what we see. So we want to crop that out, and we have the cropping tool and reset and all that. Couple of things we want to be aware of. This is the raw video file. So we know what we're looking at, and this was taken July 19th last year. This is the video dimension, 1024 by 1280, which the camera manufacturer says that's the best compromise video dimension for what we want to do and how we want to proceed. So nothing to memorize or anything like that, but we play with all these settings here. I've moved them around a little bit, and you start to see a little more of the color of the machine. It's not just grayed out or blued out, actually. So we didn't have to do any rotation. We've changed the brightness and the contour, and we've clipped off that number at the bottom that's going to be counting up for us. We go to frames and elapsed time. So what we're going to try to do is, well, we need to put in the capture rate of our camera. In this case, it's 1069. If we're using a cell phone camera, it might be 100 or 240 or 120 instead of this 1069. So I have a very high speed camera, and it's going to generate a lot of information. What we're going to look at, we're going to have the ability to take about 8 seconds worth of data, but we don't need it all. Did a little study last year and the year before where I went through and I went 1/4 of a second up to half a second and 1 second, 2 seconds, 3, all the way up to 8 to see how the animation changes. And the animation looks pretty much the same from 2 up. And so the minimum we'd like to set is capturing 2 seconds worth of data. So we have our elapsed time down here. I set it to 3 seconds for this. I just wanted to see the difference. And it just took a little longer to process, but it's something that was really easy to do. The one thing that we'll talk about when we go through the NXT software, this frame count is important. And we're going to make it store it in the wizard in another location so we can get back to it if we had any question what the frame count was. But 3 seconds of data is 3,207 frames at 1,069 frames per second. Okay. We're going to set grid points. Now, I could do calculations on the 1.3 million pixels that are in this area, in the 973 by 1273 frame. There's millions of pixels. In grid points, that's only about 7,350 in the X direction and in the Y direction. So we're going to generate time waveforms in the X and Y directions, and we're going to do it for every point on the screen. So we don't need 1.3 million pixels moving around to diagnose a problem. This one will interpolate between this very dense group of points. So we'll get a very good smooth animation without all that jerkiness to it. So we're gonna set these points. I always err on the high side because I like to have really good resolution. We're gonna click the button that says extract time waveforms, and it's gonna ask us to scale the distance. The image on its own needs some type of internal scale so that we can see how much vibration there actually is. So 3-step process. We click set distance. We draw either a horizontal or a vertical line. In this case, the vertical line is going to be very uniform for this angle that we're looking at the machine. And I need to type in what the diameter of that bearing housing is, and it's about 8 inches. Okay. We generate what's known as a magnitude histogram. And this histogram was very useful in the past. It's not as nearly as useful as, or uniform as I would have liked, but we have some background residual background vibration removal tools that are really good. So I rarely use this anymore, unless there's something really moving that isn't supposed to be in the frame. Then I can adjust things a little bit. But it's something you can play with. If you pull these sliders over, if you have a really low vibration and very few of them, you'll see little pockets, little shiny spots maybe that go away as you start to pick away at this side of the histogram. And just the opposite, high vibration, very few of them are on this side. So you'd have little shiny reflections, things like that. I had one clip where there was a guy in the background on the other side of the room, and he had a flashlight and he was looking for something, and the flashlight was moving around. So in this video format, that flashlight was huge vibration, and we couldn't clip it all out, so we had to retake the video. But there's always a place for things. This might be useful in some circumstances, but usually I just kind of skip it. When I do skip it, I get into what they have as the 6th step of the wizard, the point graphics, and I want to see an orbit. I have the end of the shaft. This is a boiler feed pump in a fossil fuel plant, and it had some vibration levels that they wanted me to take a look at and see if I could verify that with respect to accelerometers. They have a mounted accelerometer right here. So I have a horizontal vibration. I think there's a vertical one in here, but I can't see it. It might be right here. But we had some information. We could compare the video to the traditional accelerometer analysis. So I can click some points of interest, and here I just clicked on the middle of this round structure, and I checked off the orbits, and I want to see what an orbit looks like in this application. Okay, I hit the finish button, and oops. Oh, I hit the button too many times. Sorry about that. See, there's my dot in the middle, and this is the orbit that's generated at 3,600 RPM. So the speed of the shaft in my boiler feed pump is 3,600, and and we're looking right at the end of the shaft, and this is the whirl, how it's moving inside the bearing clearances. Okay, I can do an animation in the time waveform, or I can do an animation in the DFT digital Fourier transform. This is an envelope, and one of the things I have a hard time getting used to is the amount of vibration coming off of this. So 7 mils of vibration is pretty high. I haven't converted this over. One of the problems with the VES software is the conversion of things. We can differentiate and integrate the signal to go back and forth between displacement, velocity, and acceleration. We can change units, but it's more menu oriented, drop down menus, a little difficult to get to. And I'll show you that when we get to the NXT version of this and how much easier it is. This is a magnitude envelope. This peak is not at that point. This envelope is showing us the largest response in the machine at a certain frequency. The biggest peak is probably right here. This is an oil temperature measurement that's drilled into the housing, and there's an oil leak that's associated with this, and this thing really moves. So it's resonant at 3600, which is not a good thing to be if that's the rotating speed of your shaft. So he's probably cracked something or loosened up because of the vibration. So we got an oil leak. But pretty high vibration. 7 mils is on the order of 0.8 inches per second. And I think that's what we have vertically here. And we have about 0.4, no, we have 0.5 vertically, we have 0.4 horizontally. And we'll get to that in a second. Okay. So I can pick another location, and this is at 4650, and I have no idea what this is, but I'm picking it up in the video analysis. It looks like a second mode of this oil measurement, temperature measurement, or there's something going on with the blanket, the thermal blanket that's on here. So I get a lot of flicker, I think, that's coming off of that, and the software interprets the pixel changes in color as vibration, and there you have it. We get a different horizontal response. So this is a little cleaner vibration because there's not 2 components to it. This is a rigid body horizontal response. And I have some other rigid body motion down here. So the real problem with this is the 3600, because that's the biggest response, but there's also littler, smaller responses buried in here that we can always delve into. And this is, I've selected 3 different locations that I can tag, and these are magnitude and phase tags, and somewhere on the 2 to 4 mils vibration. And like I mentioned, when you do the conversion, it's about 0.5 inches per second here and 0.45 here. This is the same project. We're going to just use the MEscopeNXT shell and show you what the differences and what the similarities are. But it's going to be the same piece of equipment. We have a little more capability here. We can acquire video directly from the camera. If we plug that into the computer, we can pull one of those right off the camera card. We can look at raw video from file. That's 99% of what I do. I download all my images. Or third, we can just open up an ODS video project that's already existing. Like here I have ODS video, not very cleverly named, but it's one of my recent projects that I could look at as if I want to. So I'm gonna go to the raw video from file, and I'm gonna open a raw video. And here's the rotation, the brightness, the contrast, the cropping, all that. So let's open one up. It comes in through files, and here I have my boiler feed pump. I've left the rotation alone. I didn't need to do anything with that. The brightness and the contrast were adjusted, and actually this looks better than the VES version of this, and I don't think there's anything different. It's just that I changed the contrast a little bit more on this one. We cropped off that label down here that was counting up from 0 to 8 seconds, and it gets rid of that. And remember, I said, you know, anything that's flickering or doing anything like that is vibration in a video format. So we got the picture the way we want it. We're going to put in our frame rate, 1057. Our elapsed time is 3 seconds. So the space between these two slider bars is frame count is 3171, and that's 3 seconds worth of data. Okay. I'm going to, there is one other thing, check frame validity. There's an issue with cell phones. Right when they start up in slow motion mode, they haven't spun up to the slow speed yet, and it's a little jerky. So right at the beginning of the sample period, we want to eliminate some of that time. So our data is in between here, and we're trying to park ourselves with 2 to 3 seconds worth of data in between the start transient and the shutdown transient. So even if you're touching the screen of your cell phone, you're moving the tripod a little bit, and it'll rattle. So if we're given enough time to transition through that, we'll get the good data. So there was another thing, while it's changing from a slow, a speed to a slow-mo speed, we wanted to check those frames. So there was something they did was run through all the frames and see if there's any problems with them, and and then you can continue to adjust the elapsed time or the frame window and fix that problem. But I think there were some other fixes they used, and this really doesn't work anymore. It always says it's okay, so, which it is because we fixed it. So this will be removed from further software updates. Number of points. So I put my cursor up here on the higher end, very similar number of points in this application. And we're going to extract the time waveforms for each one of those points in the X and Y directions. So we hit on that, and usually for a high-speed camera that might take 3 or 4 minutes to process all that data. For a cell phone, it'll take about 1.5 minutes, maybe less than a minute. So it's pretty quick. We're gonna put a known dimension on our drawing so that we can size or scale the vibration properly. So we're gonna press the set distance box. We're gonna draw a line from point to point here that's gonna be 8 inches in diameter. So I put an 8 in there. I make sure this says inches, and we have proper scaling. Hit the next. Here's our magnitude histogram. Looks a little bit different. I had some slight variations in the how I crop the data and things like that, but pretty much that's what it's going to look like. And as I mentioned before, I don't change it very much unless there's something really drastically bright in the background or something's moving in there that you shouldn't be. Now this, speaking of stuff that moves and shouldn't be, this is a cable, a braided cable. This is a pipe. Here's another pipe, but they're all connected to the bearing housing somehow, and they're all moving that way. So you really can't consider them background noise. I did put a point in here and tell it I want orbits, and it's making an orbit for me. Did I skip that? Yeah, I think I skipped it. Sorry about that. There's a step in there with the wizard that I skipped. It was putting in the point and then checking orbits or vectors or magnitude and phase or point location, stuff like that. Here's my time waveform. and it's usually, it's all the frequencies at once, so it's a little jumbled in there. It's not super useful for vibration analysis. When you do the discrete Fourier transform, you can look at any peak you want, plus in this case, we have an envelope that shows us the highest occurrence of anything. It'll show us the noise floor too, which can be problematic, that the noise floor swamps our signal that we're interested in. In this case, our 3600 has popped out. We still have this 4650, and we still have some lower frequency stuff in here. So here's, put my cursor on here. I'm making an orbit that is very similar to the VES software, and went to 4650, and I remember that we had a response horizontally, and we had a vibration that was probably the largest vibration is that oil temperature piece of hardware. Now these I converted to inches per second. So I have my time waveform, and I have my amplitude and phase in the DFT envelope. The thing that's really important to me for this is the frequency spectrum at 3600, and that's where I've parked my cursor here, and it says 0.00267 inches. So 2.6 inches is the highest vibration in this image. And again, it's not where we picked our locations. It's probably right there. Something I don't normally care about. If I'm trending data in a plant, I'm going X, Y, and Z on the bearing housings. I would never look at the oil temperature equipment that's drilled into here, unless it was, in this case, it was making an oil mess, but that's not something we'd be interested in. Instead of 1 inch per second that it has here, it's 2.67 mils is roughly equivalent to 1 inch per second. I'm seeing 0.58 inch per second vertically, and it looks like 0.432 horizontally, measured at this transducer. And we took some data with that transducer, and it was very close. It was a 0.45, I believe. This is the ODS-FRF. So before, this is just doing, come on, there we go. So I'm getting the digital Fourier transform envelope, and I'm looking at what this amplitude is. So overall, it's about 1 inch per second. Okay. If I do the ODS-FRF calculation, I will calculate the phase all the way across the spectrum, and most especially the phase at where I'm trending. So if I'm trending my data at 3600, I will have a repeatable phase. So in the future, it's good for cleaning up the noise floor as well, smoothing out the noise floor. But if I do the ODS-FRF, I can trend vibration on the same machine. When I do this function and it calculates all this for me, it calculates the phase with respect to some reference on the machine. So let's say my reference point is right in the middle of that bearing housing. Okay. If I went back the next time, put my tripod in the same place and took this video, I could go in and click on that point as my reference and calculate a comparable ODS-FRF. So now the amplitude from one survey could correspond to whether the machine's getting better or worse. Okay. Video-wise, you don't get that in the DFT. In the ODS-FRF, you do have that. So we have plans for a lot of trending in the future, and this is a very easy way to get it. And I think Vibrant's the only one that calculates the ODS-FRF. Okay, a couple of NXT applications. This MEscope ODS Videos Analysis performed by Full Spectrum on a gasoline Jeep engine. And this basically is rigid body motion of the engine moving on its mounts while it's idling. And took it from a couple different directions. Video clip was captured with an iPhone video camera. The frame rate was 240 frames per second. Slow-mo conditions, 1080p, HD, all that stuff. The thing is, there's a slow-mo option in your iPhone and in your other Android phones and things like that as well. The frame rate is what's really interesting. The frame rate is just high enough to grab about a dozen different problems. So unbalance, eccentricity, mechanical looseness, cocked bearings, bent shaft, coupling misalignment, all kinds of different things like that. Those are the main problems in vibration analysis. And mechanical looseness type A is what you're seeing up here at the top. This whole engine bouncing on its mounts is just either good or bad depending on the amplitude, but it's a looseness condition, a give in the machine. And to see this clearly, I can see that there's some motion in this plane that I'm not going to get in that plane, but it's pitching a little bit. So when I go in the front location, looking at the engine directly, I see the pulleys, the drive pulleys, the belts. I have both a horizontal motion that's hard to see in this plane and a twisting motion that you see in both planes. So two views are required to get a better estimate of the engine rigid body motions. Okay. This is where we started with the DES software. We have time waveform that's generated for all the pixels or all the grid points in the structure. A DFT digital Fourier series or Fourier transform is generated, and each one of these peaks has a different motion in the engine. And we could walk through them all. Oops. We could walk through them all, but take a little bit too much time. This was a little over 1,080 CPM. So it's one of the rigid body bouncing modes in the engine. This is the time waveform. And it looks a little clunky because I had to slow down the waveform or the speed of the sweep so that we could actually get some amplitude response. And it's slow and what have you, but that's what it looks like. So there's not nearly the exciting end of things in the time waveform. The frequency spectrum is really interesting. Now the DFT, it's only collecting data. It only has one average, and it has phase for this application because all the time waveforms are captured simultaneously. But comparing this phase to the next survey, let's say position 1's out here, and I'm taking this video. The phase will be completely different in the next one if you're using the DFT envelope. If you're doing the ODS-FRF, you're going to use the same reference point, and the phase will be meaningful. You'll be able to see the differences in the video and differences in the amplitudes in a clear way. This is, which is just used in the NXT software right now. The top plot is what we saw in the DFT envelope. So I can still see my peaks. I have noise that's generated that I should be able to get rid of if I do the ODS-FRF, and it turns out we have. This is 0.01, which runs along here. This is down under 0.001. So we've dropped the noise flare an order of magnitude. We're still seeing our peaks. We're just seeing them a little cleaner. So two different measurements, easy to do. And if you're trending, this is the way to go, the ODS-FRF. If you're just looking for machine response, you can use the time waveform or the DFT envelope and park yourself on one of these peaks and you get a good idea what the motion is. This was an application, and again, I do most of my work with an iPhone. So I can take video, 15 seconds of video. I have some parameters that I'll show you in a minute, but 15-second of video, you can email it all over the world, basically, and you could have collaboration. I have a couple guys that work for me. They go out and they get videos, and we all look at them, and you get really good at doing this type of analysis pretty quick. So the MEscope ODS videos analysis performed by Full Spectrum. This is piping in a refinery application. In the wintertime, you can see the snow on the ground. The video clip was captured with an iPhone camera. The frame rate was 240 frames per second in slow-mo 1080 HD mode. And the processing here is with the NXT software. The piping was completely inaccessible with respect to traditional vibration analysis due to the pump and piping insulation jackets and the stainless steel or non-magnetic material that was everywhere. So I could not take a measurement with my magnet-mounted piece of equipment. There were some bolts right here, and these are my two triaxial accelerometers. The only way I could get them to stick to the stainless steel structure was to add a nut on the end of these threads coming out of the ground. So this is basically the pump, and it goes down another floor. This is an angle bracket that's holding the pump in place. And on top of those threaded rod, basically, I could screw a magnetic nut in there and put my transducers on it. Horrible placement. You don't know what the attenuation is from the pump all the way through its shell and into the bracket and into the transducer. You're basically measuring foundation and trying to get an idea if the pump has a problem or not. All this is aluminum jacket, stainless steel wherever the fittings are, and it's, the pipes, you got a 2-inch pipe and you got a 8-inch jacket on it. You can't take data on this and get good results unless you have a video camera or a cell phone. So I took a couple cell phone shots and processed them. And this is at turning speed of the pump. It was 3,100 RPM, and it dances around quite a bit. And remember, it's scaled way up so you can see the motions. But it really moved a lot more than I thought it would. Collection of a digital Fourier transform includes a single spectrum average, okay, if you want to remember that. So we're just taking one measurement, boom, and creating a frequency spectrum. In the time waveform, you can animate that. They're all phased together, but you can't compare that one survey from the next. So if I went back next month, took the same image of this piping line and pump, it would have no phase relationship to what the first measurement had. I'd still have some amplitude. I can still animate it, but there's a better way around this, is to generate the ODS-FRF. So the calculation of the ODS-FRF allows additional averaging and overlap processing, which helps reduce the noise floor. And most times it's about an order of magnitude. So the peaks kind of pop out of the floor a little bit better. In addition, unlike the DFT, the ODS-FRF also calculates a unique phase response that can be compared to future video measurements as indications of change for machinery monitoring. So something to think of in the future if you're getting into this technology. This was another job that we have a little service that if you send an email, 15 seconds worth of data, we can process it for you. And so we've had lots of customers they want to see how this works out, and they send their video. We process it and say this is likely what's happening, and if they want us to get involved further, we are. If not, they have something that they can see, and they can, if they're interested in it, they can get their own equipment and software and start doing it. And this was apparently there was some debate in the plant of what was causing this, and one guy thought it was the belt was misaligned, the other one thought the motor was misaligned, and it turned out the floor was flexing. So it's a pretty thin floor. It's a diamond plating. They didn't have their support beams in the right location, and the floor was bouncing up and down, as you can see. So the first image here is just the normal exposure, and you can see how it bounces. It's enhanced a little bit by putting the color contours on there and seeing how the floor is bending underneath it. So a lot of motion, and it's stuff that you just can't see. And every day I see something different that I've never seen before. I used to say that about normal vibration. Every month I see something that I haven't seen, and I've been doing this for 32 years. Now with the video stuff, it's every week, every couple of days I see something that's just kind of blows my mind. Very interesting field. This was one of the guys that works for me. He did an analysis on a fan in a plant, and direct coupled. This was one of those tire couplings, and he put a marker on either side so he could tag the magnitude and the phase. And I can barely read that, but he has an out of phase motion across the coupling, and in this case it indicates that you have a coupling misalignment. Out of phase behavior at 1 times RPM verified visually and via mag phase labels across the coupling. We couldn't remove this cage that was guarding the rotating shaft, so we got direct measurements right on there with a little close-up. Turned out really well. If we had, instead of an iPhone, if we had a high-speed camera, it's usually too dark to see in to this level. It's amazing how much light those suck up, but you can't get enough light on them usually. If you were interested in sending me a video, a cell phone or camera capable of filming at 120 to 240 frames per second, iPhone series recommended for consistent results, 15 seconds in a slow-mo video setting. Your phone should be standing as still as possible. So tripods are the best, not required, but if you want to get a good response, lean the phone against something and hold it against whatever you're leaning it on, and then take the video and see what you get. If you try to hold it, your hand will bounce all over the place, and it makes a difficult analysis. Multiple videos, different vantage points. Usually we charge $500 for 3 to 4 videos on a machine. So you get a little report, and it's cheap. And if you're interested in doing more, that's one thing. If you want to get your own MEscope ODS Videos software, that's another. I think there's, correct me if I'm wrong, Mark, but you can get a demo software for like 30 days.
That's correct, yeah.
Yeah, so if you guys
on the store,
if you're interested in that, it's a great way to learn. It's on-the-job training. It's pretty inexpensive, and then you can repeat what I did or what one of my guys has showed you in the little report that comes with it. If you have an iPhone, I think you're in good shape. If you have a Samsung Galaxy or any of these LG phones, they have, they're different companies, so they have different cameras, and it's annoying that it's not as uniform. But the iPhones are all have slow-mo at 240 frames per second. I imagine the best quality one is the 13, but they're all gonna work. That's all I have for today. If you have any questions, I'd be happy to answer.
We did have one question, just asking about, is the motion in the video amplified somehow? And I mentioned it was to the group, but I don't know if you want to elaborate on that.
Is it amplified?
Yeah.
It's enhanced. Yeah,
right.
It's rescaled so that you can see it. And you put your cursor on that peak so you can find out how many mils, how many inches per second, how many G's that is, and on a magnitude scale. But yeah, the reason we basically scale it up is so you can actually see it in the video.
Mm-hmm. Mm-hmm. If you get any other questions, feel free to type those questions in here. We got a little bit of time here. We can get your questions answered. Another comment here about tripods with a USB clicker. There are tripods that are sold with a Bluetooth USB clicker, so you can actually start your video and stop your video remotely. You don't actually have to touch the camera, so it just eliminates any kind of flicker at the beginning and end of your video. So those are real cheap. Those are available on Amazon. You can find those anywhere, but just another way to utilize your cell phone for conducting ODS videos. Yeah,
well, usually that's why I do the 15-second rule, so that I can get 10 seconds out of it. So when you touch the button on your phone, everything moves, and it's amazing how much. But if it settles down in that 15-second time frame, then you can crop it out as you're processing your data. So maybe take 8 seconds, and you're taking 3.5 seconds off of each end for settling.
Another question: how does the phone compression of the image affect the data?
The phone compression, there's a very minor phase shift. I can't remember what it is. It's less than 5, less than 10 degrees from top to bottom. If you're thinking about the way that it's stored in a cell phone, it scans it across the screen top to bottom, and there's a slight phase shift from the top of the image to the bottom. But we're looking at phase requirements plus or minus 90 degrees to show a problem, or excuse me, plus or minus 180 degrees to show a problem. You really don't see it in this application. As phones get better, in fact, some of the tablets, there's no phase shift whatsoever going top to bottom. Maybe I didn't answer that the way you wanted. Let me know.
Next question here: how high a frequency can you measure with a cell phone video? Great question.
Well, if you capture at 240 frames per second, you can look at your data up to 120, which is, it sounds, oh man, that's no good. But remember what you're looking at. You're looking at motion, okay? If you have an unbalance, you're looking at a heavy spot going by. If you have a misalignment, you're looking at a coupling. There's a push and a pull, 2 events every revolution, okay? And those are associated with what kind of motor you have. The highest frequency motor is a 2-pole motor, and it's running at almost 3,600 RPM. Okay, there's a slight, I don't know what you want to call it. It can't run exactly at 3,600, so it's just a slight change from that. If you go twice that, because you're looking for 2 events per revolution, you'll be just under that 120 CPM limit. So basically the F max for frequency analysis is 120 hertz, or 7,200 CPM. But any other motor, 4-pole, 6-pole, 8-pole, 10-pole, the rotational speed starts going down from there. So the one that's as closest is the 3,600, and you can still get that. There are some things that, obviously a lot of faults above that frequency range, but they don't translate themselves into motion in the entire structure. Like if I had a blade pass frequency that was, 10 times higher than rotational speed, then it's pulsing, but it's not making the structure bend and flex and twist. When you're looking at misalignment or cocked bearings or bent shafts, they're moving the bearing housings. You're seeing a mode shape. And the video capture is perfect for that. So it is kind of amazing that somebody at Apple decided to go to 240 frames, because it's almost ideal. I assume we'll get a 480 frames per second next time, and it'll capture a little bit more, but not as much as you think. There's a dozen problems in that subsynchronous to turning speed range that we have now.
We have a request to mention AVD cursor in NXT.
Oh,
I don't know if
yeah.
we can, if you can pull that up for us.
Well, I was going to see if I had something. Okay, this
You
is.
want to describe what that is?
Yeah, this is that fan that we just looked at, and I redid it in the software because I thought it might be useful, which is kind of nice. These are in inches per second, as you notice. So I have at location 4109 X and Y, I have in the X direction it's 0.819, in the Y it's 0.842. So that's the motion at this location on the motor. This one 0.309, 0.819. So inches per second. Okay. There's I can't see it because there's some control panel here. Oh yeah, I can. Hold on.
You can move that.
I can.
Is it the
Oh,
go to webinar control
there
panel?
we
Okay.
Yeah, I moved it so I
Yeah, there we go.
didn't have to see it. So yeah, the webinar thing is in the way. Okay, I got it. I think if I go here, there we go. So I have this cursor. Here's 1790, which is the speed of the motor. As it comes into the software, it's 3.74 mils. So we're measuring displacement of pixels, basically, in grid points. So if you have displacement here, we want to change that, and you normally would have to do a process where you divide the entire spectrum by frequency to generate a different entire spectrum. In this case, we're only doing that on a single frequency. So whatever the cursor's sitting on, 1790, it's 3.74 mils. I can go to velocity, it's 0.7 inches per second. I can go acceleration, and it's 131 inches per second squared. And that should be in G's, but it's the proper conversion, different units. So if I go back to velocity, it changes all the labels. If in addition to the point at your cursor. If I go to displacement, I have 3.74 mils. Here I have different locations than the overall level. 4.3, 4.5 so far in mils. So mils aren't really useful in vibration analysis because they don't, you're trying to compare a location on your motor or your fan or what have you to 0.3 inches per second. Kind of the standard in the industry is if you're monitoring something, it goes above 0.3 inches per second, there's some kind of problem, you need to go and investigate. You're not going to get that from looking at mils. 4.3 mils means nothing to me. If it's a low speed shaft, it's acceptable. If it's a high speed shaft, it's very unacceptable. So you always have to try to figure out how it relates to velocity. If you go in here and just hit velocity, you know, at 0.7 inches per second, you have a problem. Okay. And we can put our color contours on, and we need a little more definition on the color contours, little color key. But these also will change. So they will be, they'll move with the inches per second here. And that's, I realize it says 7 inches per second, but there's something flexing in here that I didn't get rid of as background noise. That's causing that very high vibration scale. Anyway, is that good enough, Mark?
That's good. Yeah, yeah. Any other questions?
The other thing here I didn't mention, this is the envelope. So it says DFT envelope. I can go into any location, and you'll notice there's a lot of locations where there's nothing there, just noise floor. I got this little peak that's trying to stick out, and it makes it hard to do. If I change this to an ODS-FRF, then a lot of this noise floor goes away, and you can see the peak more dramatically sticking out of the floor noise. Good enough for that. I assume by the time we have another one of these webinars, I'm going to be all over this NXT stuff, and we'll go through multiple analyses. And hopefully, some of you guys will mail me a video, and I can play with it. And you know, if you get your first video up here, we ought to give them a T-shirt or something. I don't know.
Absolutely, absolutely.
T-shirt.
Yeah, if you have a video that you're able to share, please send it on over. Dan's email is modalguy@aol.com. You can reach me at mrichardson@vibetech.com, or always you can reach us out, reach out to us at sales@vibetech.com if you have further questions, or if you want to get a quote for some software. You can always, as Dan was mentioning earlier, on our website we have the Vibrant store, and if you wanted to purchase a 30-day license for ODS videos, you can do that right off of our website. With that, I think we're about done, Dan. We will get another one of these spun up for you here, and so stay tuned to your emails. Any last words?
No, I'm good. Thanks
It's
for
76,
coming.
76 and sunny in wherever Dan is in sunny Florida. About 25 degrees here in Denver, Colorado. So I think we need to move out to Florida here for a few months. Looks pretty good. All right, with that, we'll let everybody go. And again, we will get this spun up to our YouTube site. And I appreciate everybody for joining us, and we will see you next time. Thanks, everybody.
Thank you.